Alright, welcome back to our Chapter 3 sections. We're going to get in another technique of finding derivatives, which in Section 3.7 we will refer to as the chain rule. And actually in all sections we'll refer to as the chain rule, but that is the name. So with the rules presented so far that we've had for our shortcuts with differentiation, we're able to take care of many functions, but not all of them yet. So the rules that we've learned are not able to find derivatives of composite functions. So, for example, let's look at a composite function. So I'm going to say, if I have, let f of x equals, say, x cubed, and g of x equals 5x plus 4, then what is the composition of those two functions? Well, we've already kind of gone over this with composites, and so basically we're taking this g function, putting it into the f function. So we're taking this g function, putting it into the f function wherever we see an x. So that is taking the 5x plus 4 and cubing it. So looks like a power rule, but it's not fully a power rule, because now instead of just having a variable here, like what we've had before, we now have an expression. So we have to adjust for that when we have that expression. Now, I could, if I wanted to, write this out 3 times and FOIL it if I wanted to, which is also referred to as expanding that binomial. Then I can use the power rule like normal and be good. But what if I had something like this, where the composite was 5x plus 4 to the 100 power? I definitely would not want to go and multiply that out 100 times. That would be very long and very time-consuming and tedious. Lots of places for errors. So this is where the chain rule comes into play. When we have some composite functions, inner and outer functions, I would call this the inner function and this to be the outer function. Now we're going to suppose that y is equal to f of u. It is differentiable at u equaling g of x, and that function, u equaling, u equaling g of x is differentiable at x. The composite function that we will state is y equals f of g of x is differentiable at x, and its derivative can be expressed in 2 different ways. One of those ways we could write in terms of dy over dx. So I would have dy over dx would come from taking the derivative of this one with respect to u. So I would do dy over du, and then I would times that by taking the derivative of this one with respect to x. So it would be a du with respect to x, so that would be over a dx. So that's one way to do it. That's not normally the way that I like to see it. This is more of an implicit fashion. The way I like to see it, though, is with the functions, the actual f and g of the composite. So we'll write it down this way, that the derivative with respect to x of f of g of x is equal to taking the derivative of the outside function f in terms of g. So that is f prime of g of x. And then the chain rule part is that then I have to take the derivative of what's inside here. So then I have g prime of x that I am multiplying by that. Okay? So it is a product of 2 things. Now, we're going to do this kind of by example. It's hard to kind of work in this terms type thing. But before we do that, we are going to refer to the g function as the inner function, like I just alluded to. And our f function is what we are going to refer to as our outer function. Okay, that should make sense with this. Inner, outer. So, what we have to do is basically take the derivative of the outer function in terms of the inner function and then do the derivative of the inside piece. Okay, so how's that going to work? Notice here I have this composite function, this being the inner, the 10 as a power being the outer. So that is a power, and by the power rule, in order to find the derivative of that with a power rule, I have to take this 10 out front, make that 10. Now, in terms of our inner function, so this stays the same. The only thing that changes at this point is that I have to decrease that power by 1. So that was just like if I had a y here. That would be 10y to the 9th. Now I have 10 times this expression to the 9th power, but now I have to do what we have is that g prime of x. So now I have to take the derivative of the inside piece. Now, the derivative of 6x cubed, bring the 3 out front, gives me an 18x squared when I reduce that power by 1. And then we have a linear term, so that is just going to be plus 3. Derivative of a constant is 0. Don't have to worry about that. So that is the chain rule apply, but I will tell you that most often than not, we kind of factor things out. Not so much inside here with this to a power like that, but definitely on this chain rule part, if there's something that is factorable in common, then please do so. So like for instance here, there's a 3 in common. So I could take a 3 out and make that 6x squared plus 1 to change that. And so now I could combine this 3 with that 10 and write that as 30. I'm going to go ahead and write with this expression of 6x squared plus 1. And then in with my trinomial, 6x cubed plus 3x plus 1 to the 9th power. And that right there would be my final answer. So make sure you simplify it down as far as you can when you're working with the chain rule. All right. Now, by no means do I, ask that you multiply that out 9 times. That's just ridiculous. We'll leave it as a power. All right, so let's look at this next function. Notice I have a square root. That is the outer function. This expression is the inner function. Now, I'm going to actually rewrite this. In order for me to be able to use the power rule, I must change that power to a 1/2 versus a radical. Okay, so take that radical away, make that a 1/2 power, and now we are good to go, ready to do our chain rule. So notice we have a power rule on the outside. We have this polynomial on the inside. We're going to take care of the power rule first. So I'm going to bring the 1/2 out front, keep it in terms of that, and decrease the power by 1. So that looks like 1/2 times 5x squared plus 1. Now, when I decrease that power by 1, 1/2 minus 1, or 1/2 minus 2/2, is negative 1/2. And that is just this part of the chain rule. Outside power out front, keep it in terms of the expression, decrease that power by 1. Now I have to go to the inside function and take care of what is the derivative of 5x squared plus 1. And we're going to times that by that. Well, this becomes a 10x, and that's a constant, so that part is 0, so I basically just get a 10x there at the end. Now is the time to simplify. So when I simplify, notice I have a negative exponent that I'm going to choose to write in the bottom as a 5x squared plus 1 to the positive 1/2. And the other pieces that I have is this 1/2 times this monomial 10x. Well, half of 10 gives me a 5, and those two things, don't forget your x, those two things would then occur on top. Okay? All right, very good. Let's move on to the next problem. This is another power rule problem because the outside exponent is a power. And we have an expression on the inside, so the inner function is 5x plus 4. The outer function is this x to a 3/2, okay? So we are going to take the derivative of the outside piece. So we're going to bring this power out front, gives me a 3/2. Now remember, keep that 5x plus 4 the same. Decrease your power by 1. So if I decrease that by 1, which is the same as 2/2, then I get a 1/2. But then I have to turn my attention to the inside and take the derivative of what's on the inside. Now with that being linear, that's just going to be a 5, and that's going to be a 0. So I have to add in a multiple of 5 here for that. So to finish off the way that I would write it and end with, I'm going to do a 3/2 times 5. So 5 over 1, 5 times 3 is 15. 2 times 1 is 2. And then I have my 5x plus 4 to the 1/2 power. So remember, in calculus, we don't really care too much about radicals. We go ahead and keep our answers in terms of powers. That's why I'm going to keep it as a 1/2. So it would not be incorrect if you wrote 15/2 times the square root of 5x plus 4. That would be perfectly fine as well. All right, let's do a couple trig problems and then we'll get to a quotient. We haven't done anything yet with our product or quotient rules that we learned. earlier in chapter 3. But here, this is a trig function that is cubed. So I'm going to rewrite this. With that power of 3, remember, the shortcut way to write this trig function to a power is that I bring that little power inside in front of the angle. This is another way to write sine cubed of x. So I like to see it this way when I'm working with the chain rule, so I don't forget about decreasing this power by 1 in terms of this function and then going back and doing the derivative of that. So let's see what we have here. We're going to do the power rule. Bring the 3 out front. Keep that sign the same, remember, and decrease your power by 1. That's the outermost function that you have, just like any power rule. Then I have to go inside and take the derivative of this. So the derivative of sine is actually going to be cosine. So I'm going to multiply that on the end. And there's really nothing we can do to simplify too much. I'm going to just bring this power of 2 back inside and write it as 3 sine squared of x times cosine of x, all without parentheses. And that's perfectly capable of being done. Okay? And that would be our answer right there. We got a little delay going on already. Alright, so here we go down to this one. Now they look very similar except for the cube is somewhere else. The cube is at the end this time versus in between the angle and the sine. So this, remember, says I need to take the derivative in terms of x. I'm going to rewrite this function a little bit for you so that it might make a little bit more sense. The cube is all in the angle. It is not part of kind of a power on the outside with your trig function. It is strictly on the angle. Alright, so if I want to take the derivative of this, here's my inner function this time, and this is my outer function. So the outer function that I have to take the derivative of first in terms of this is the sine. So I'm going to take the derivative of sine first, which is cosine of that angle. So I'm going to go ahead and keep that x cubed in parentheses. Then I have to times that by the derivative of the inner function. Again, the outside function in terms of g of x. But then I have to take the derivative of the inside function, which gives me a 3x squared. And then you're done with that chain rule. So here, this gives me a final answer of 3x squared times the cosine of x cubed. Now, here nor there, you don't have to have those parentheses in there, but please make sure that you do write it correctly, and more importantly, that you do type it into my lab math correctly as well. Okay? All right, very good. So let's go now in terms of a quotient rule. So notice that this time an outside exponent again exists. So I'm going to do the power rule for my outside function, but the inside function this time is a quotient. So we got to do a little hody-hi stuff, okay? So we're going to take the derivative of f, and the first thing we're going to take care of is that outside function. The outermost function is this cube, so I'm going to bring the 3 out front. Nothing changes inside that set of parentheses because I have to decrease that power by 2. So bring the outside power out front, keep this as is, and decrease that by 1 gives me a 2. Okay? But then I have to go inside and take the derivative of the inner function. So that's where the hody-hi comes into play. So we're going to take ho, which is 3x squared plus 2, d-hi, take the derivative of the top, which gives me a 10x, minus hi, which is the 5x squared, d-ho, I have to take the derivative of the denominator. So that looks like I'm going to have a 6x and then a 0, so it's just going to give me a 6x. All over the denominator squared. So that's going to be 3x squared plus 2 quantity squared. And that right there is just the quotient of the inside piece. So we had to learn that first before we can end up doing this chain rule business. So you want to make sure that you know how to do those products and quotients. All right, so that's the calculus. Now it's algebra to clean up. So I'm first going to clean up this upper part here. And I'm going to do that just right above there. And you can do that as well if that saves you a little time. I'm going to distribute here and give me a 30 x cubed plus a 20x, and then when I minus these two monomials that I'm going to multiply together gives me a 30x cubed as well, which is really, really nice because we have a 30x cubed up here that I can now cancel out. So all of that on the top reduces down to 20x. Now, I'm going to go along and kind of break up this power of 2. I got to give a power of 2 to every term there. So I'm going to treat this kind of as 1. And I'm going to go ahead and multiply or bring in that power of 2. So I have to do a 5 squared and I have to do an x squared squared. But I have this 3 out front. So I'm going to go 3. 5 squared gives me a 25. X squared squared is an x to the 4th. All over this quantity squared. Again, no need to expand it out. Just write it as quantity squares. Now, what I then turn to is the quotient rule part where I have that 20x on top all over this 3x squared plus 2 quantity squared as well. So, it takes a couple steps with algebra to kind of get it down to what we need to. And so, once I have that, now since everything is just multiplied across the top, I can multiply all those. There's no plus or minuses. And these are the exact same two expressions. So, I can treat that as a 3x squared plus 2 quantity to the 4th because I have 2 in the first and 2 in the last. Therefore, I have 4 all together there. Then I'm going to multiply my numbers up top. 3 times 25 is 75, and 75 times 20, I believe, according to my notes, is 1,500. And I have an x to the 4th and an x. So when I combine those together, it gives me x to the 5th. So that right there is our derivative using the chain rule where we incorporate a quotient as well. Okay? All right, very, very good. So again, be meticulous. Do the correct part whenever you need to do the calculus, then use algebra to get down to a final answer. All right, let's turn our attention to a different type of problem where I'm going to be giving you a function in terms of f and g, and also, or f or just g in a case, and then this table over here, and we are asked to find multiple pieces of that. So let's see what we have. If I end up looking at h of x is equal to f of g of x. Now, according to our definition that we have on the previous page, I'm going to write above here what is the derivative. Remember, we take the derivative of the outermost function, which looks like f prime of g of x, but then I have to take the derivative of the inside piece, so I have to multiply that by g of x. So that's what we're going to do for parts A and B, to find out what h prime of 1 and h prime of 3 are. So let's do that, and then we'll find the k of x, k prime of x. So I'm going to take 1 and put it into each one of these because my chart's only in terms of f and g. So I'm going to say, okay, if I have h prime of 1, that is defined by putting a 1 in here and a 1 in here. So f prime of g of 1 times g prime at 1. And from here, it's just basically looking at my chart. So this is kind of getting you more of the abstract thinking of taking derivatives because it's not an actual function that they give us. The charts business isn't too bad. All right, so let's first find the g of 1 on the inside for this composite. So g of 1 is going to be 4. So I need to now figure out what is f prime of 4 times g prime of 1. Well, now I'm looking at my derivatives. F prime of 4 is 7. And g prime of 1 is 9. So this means I'm going to have to take 7 times 9, which gives me a final answer of 63. Now let's do the same thing with h prime of 3. I'm going to put 3 there, or I have a 3 there, which means I need to put a 3 there and put a 3 there. So I get f prime of g of 3 times g prime of 3. So we need to go to our inside functions first. So let's do g of 3. G of 3 right here is 5. So I need to figure out what is f prime of 5 times g prime of 3. And when I do that, going over here to f prime of 5 is 2. that I have to now times with g prime of 3. G prime of 3 is 3. Therefore, 2 times 3 does give me a final answer of 6. So again, not terribly hard to do any multiplying, but you just have to know which numbers to get that multiplying done. All right, let's look at C and D. That is the function k. So if I'm looking for k prime of x and it's a composite function, then that means that I need to take the derivative of the outside function, which is going to be g of x, and then put my equals there, take g prime of g of x, and then take the derivative of the inside piece, which is multiplying by g prime of x. Okay, so when we do that, finding the k prime of 3 and k prime of 5 is going to be just like what we did here. I'm going to take this 3 and put it in there and put it in there. So when I do that, I get, okay, so g prime of g of 3 times g prime of 3. So this one's got a lot of g's in it. Make sure that you watch those. So I'm going to go to the inside piece here. And what is g of 3? It is a 5. So I now need to look at what is g prime of 5 times g prime of 3. Now we go to our attention over here now in the g prime function of 5 is going to be negative 5. And g prime of 3 is 3. So that means I need to do negative 5 times 3, which again isn't bad. It's negative 15, but knowing when to get those numbers is important. So then now if we look at k prime of 5, I'm going to put 5 here. The 5 is there, means I put a 5 here and a 5 here. So we need g prime of g of 5 times g prime of 5. So what do we get when we do that? Well, when I look for g of 5 on the innermost piece, I get a 3. Therefore, I need what g prime of 3 is times g prime of 5. I believe we just did that, didn't we? Over here, we did them just in the reverse order. So if we go to our chart again, g prime of 3 is 3. And g prime of 5 is negative 5. And therefore, we multiply them together and get negative 15. So those are our answers to those types of problems. So again, they're not hard when multiplying a final answer, but getting those numbers that you need could be a little tedious at first. All right, moving into our last problem here with the chain rule, we are looking at doing a couple things here. We saw a power rule with a quotient on the previous side of our notes. And this one, notice I have two different functions here. I have this x cubed and I have this quantity to the 4th power. So that means that we are going to have to incorporate a product rule, okay? So make sure that you are able to do the pieces of the product rule, which if you recall, that is that we take the first times the derivative of the second, plus the second times the derivative of the first. So we're going to look at y prime here. Here's our first function. There's our second function. That's going to have to incorporate a chain rule when I take the derivative of this, because I've got a power on the outside and I have an expression on the inside. It's just not a variable to a power like what we have here in the first function. So for our derivative, we're going to take the first times the derivative of the second. Now this is where we have to incorporate the chain rule. We're going to bring the 4 out front, keep the expression exactly as is, but decrease that power by 1, and then go to the inside. Then I have to take the derivative of this, which ends up being just a 2x because this goes to 0. So that is just the first term of our product rule. Again, taking the first times the derivative of the second. The first times the derivative of this becomes that. Then I need to add to that the second function, which is x squared minus 4 to the 4th, times the derivative of the first function, which is just when we first started doing a power rule, just bring the power out front and decrease that variable's power by 1, which gives me a 3x squared. So again, that's the calculus part of it. I'm going to turn to algebra now to simplify it down as far as I can, and that's what the expectation is going to be for you to do as well, is to simplify that. So I have an x cubed a 4, and a 2x. So 2 times 4 gives me an 8. X cubed times x gives me an x to the 4th times the x squared minus 4 to the 3rd power. Then I'm going to choose to write this monomial in front of that expression as 3x squared times x squared minus 4 to the 4th. Now, this is somewhat simplified, but I do have some common terms here that I can factor out. So if you are able to factor some things out, please do so. Notice with my 8 and my 3, nothing in common to factor out. But with an x to the 4th and an x squared, I definitely can take the lower power. So I'm going to factor out an x squared. And then I have an expression in common as well. So I'm going to take out the lowest power of that between the 3 and the 4 is that cube. So I'm going to take that out. And now we have to determine what's left over. So if I take all of these terms away from this term, what's left over? Well, obviously I need an 8. I took out an x squared and I need an x to the 4th, so I need 2 more x's, so an x squared. And I took all of this expression out front. So I don't need anything else besides an 8x squared. Then, what do I need here to make this term back? Well, notice I need a 3. I took the x squared completely out, but I only took 3 of these out. So I need a 3 and I need an x squared minus 4 to make that power of 4. So if you need to, make sure that you kind of multiply this times this to see if you get this back, and multiply this times this to see if you get this back as well, okay? So now at this point, we just need to simplify this inside piece. So I'm going to distribute nothing with these outside terms here that I factored out. I'm just going to rewrite them. And this piece here, see if we can kind of save a step. When I distribute, that becomes a 3x squared that I can add to an 8x squared to give me an 11x squared. And then when I multiply 3 times a negative 4, that gives me a minus 12. So that right there would be our complete final answer for this function, in which we have to incorporate a product rule, but also within that, the chain rule for this function to a power at this point. Okay? All right, very good. So that's the chain rule. Again, adding to our toolbox of being able to find derivatives with techniques. Of course, we do have the ultimate definition, which is our limits for our difference quotients, which is the definition of a derivative. But of course, that takes a really, really long time. So making sure that you can do these different techniques with different functions is important. All right, so we will then move on to our last way to find a derivative before we get into some more applications in section 3.9. So that means that section 3.8, as you can see here, is referring to implicit differentiation, and we will save that for next time. Until then.